Greetings, Panthers. It's Dr. Augustine. We are going to tackle this bear of a titration curve. So this is a weak acid, strong base. We've already set this up before. Typical curve, what it looks like, it starts at a little bit higher pH than a strong acid because it's a weak acid, right? Start at a higher pH. It kind of goes up initially and then gets kind of flat. This is the buffer region up to the equivalence point, and then beyond the equivalence point, it goes up and saturates out. In the last video, we talked that there are four distinct regions. There's before we add anything. There's this buffer region between 0 and just below the equivalence point. And there's the equivalence point itself. That's the third region. And then the fourth region is just beyond the equivalence point all the way out to, I guess, infinity. You can keep adding stuff. And where does the pH end up? So here's a problem we're going to work on. I want to calculate the pH during the titration of 40 milliliters of a 0.1 molar propanoic acid, which we're just going to call HPR, with this given Ka value after each of the following additions of sodium hydroxide. And I think what I'm going to do in this video is I'm going to tackle A and B in this video, and then the next video will be C and D. All right, so the first one is actually a repeat of section 16.6. So if you've done 16.6, you should know how to do this. So now would be a good time to stop the video and see if you can do this problem without my help. And I will set up the problem for how to solve this right now. Okay, so the first point on the curve is actually just an equilibrium problem. You have this weak acid, propanoic acid, it's got a certain Ka, and you have not added any base to it, so it's going to be an ice table. We're just doing an equilibrium type calculation. So let's see how we approach this. We're going to have HPR, aqueous, dissolved in water, and that's an equilibrium to form H3O plus, aqueous plus propanate minus ion. Okay, this PR just symbolizes propanate. And we're going to make an ice table. Initial concentration, change in concentration, equilibrium concentration. We're going to start with a 0.1 molar solution of the propanoic acid. We have 0 H3O plus, 0 propanate ions. This one's going to go down by some amount, X. We don't know how much. It's going to go up by the same amount, X, of H3O plus and propanate ion. So we're going to end up with 0.100 minus X for the propanoic acid, and we're going to have plus X and plus X for the two products, H3O plus and PR minus. And of course, we can write an equilibrium expression for this. Ka is equal to the concentration of H3O plus times the concentration of PR minus divided by the HPR concentration. And that is going to be equal to X squared over 0.100 minus X. And that whole thing is going to be equal to the equilibrium constant, which is 1.3 times 10 to the minus 5. Okay? And you've done a bunch of these problems before, and you'll recognize if you've done a bunch of these problems that we've got a 10 to the minus 5 up here, and we've got a 0.1 here. So because there's a large difference between the 10 to the minus 5 and the 0.1, we can make the approximation, which makes life a whole lot easier. And we're going to say that X squared over 0.1 is approximately equal to 1.3 times 10 to the minus 5. Cross multiply, X squared is equal to 1.3 times 10 to the minus 5 times 0.1. And X, of course, is going to equal to the square root of this whole thing, 1.3 times 10 to the minus 5 times 0.1. And if we solve that out, X is going to be equal to 0.001140. All right, and if we recognize X is actually the concentration of H3O plus, right? So this guy is equal to the concentration of H3O plus. And of course, we know the pH is equal to negative log of the hydronium ion concentration. So therefore, this is going to equal to negative log 0.001114 and that equals to 2.94. Okay, so the first point in this titration curve is a 16.6 problem. It's calculating the pH of a weak acid with a known initial concentration and a known Ka value. So using the known Ka value, the known initial concentration, we set up an ice table and we solve this exactly like you would have done in the last chapter. And from there we can find the pH. So that initial pH is 2.94. Now the next problem is going to be a little bit more involved. Now we're going to take a look at 30 milliliters addition. And I know from this problem that's somewhere in this buffer region, 30 milliliters. So the next problem we're going to take a look at is what happens when we have more than 0, less than the equivalence point, somewhere in this buffer region. Okay, so now we've done this first point. Now we're going to take a look at the buffer region here. And whenever you hear the word buffer, Henderson-Hasselbalch equation should come to mind. Okay, you can use the Henderson-Hasselbalch equation to do this calculation. So let's start by writing out the chemical reaction. So we've got HPr, propanoic acid, and we react hydroxide ions with it. Now you might be saying, why are you not writing sodium hydroxide? Remember, sodium is a spectator ion, so we don't need to write, we could write NaOH, but we know it's the hydroxide ion where all the action is. And the other thing we know is that this is a very heavily forward-favored reaction, so we don't need to write an equilibrium sign for this one. And you can convince yourself by calculating the K values of these different reactions, but I'll just tell you that K is usually much, much greater than 10 to the plus 4 for an acid-base reaction. So this is a heavily favored forward reaction. So water is one of the products, and PR minus is going to be one of the other products. Again, spectator ion, you'd say sodium propionate. Okay, and then also this is aqueous. Now, a little bit different from the last problem. We are going to make a mole table. We're not going to make an ice table. Okay, we're going to take basically a stoichiometry table of the number of moles of these two starting reagents. So in this problem, we're going to say number of moles initial, number of moles change, and number of moles final. Okay, and let's consider the conditions we have. We have a 40 milliliter of 0.100 molar of the HPr, and we have 30 milliliters of 100 molar OH minus. All right, so that means we actually have 4.000 times 10 to the minus 3 moles of the propanoic acid, and we have 3.000 times 10 to the minus 3 moles of the hydroxide ions. This reaction's in a 1-to-1 ratio. So for every one of these that goes away, one of these is going to go away. And so this is really a limiting reagent problem, right? We're going to run out of OH minus before we run out of HPr. And because of that, we're going to end up with 0 moles of OH minus at the end because this reaction completely goes forward. And we're going to end up with some of this left over. All right, so let's fill in the rest of this table. So this is going to be minus 3.000 times 10 to the minus 3 moles. This one's minus 3.000 times 10 to the minus 3 moles. And when this goes down, this has to go up. Now we could add that amount of moles of water, but that's really insignificant compared to the total amount of water. But it is significant for the amount of propionate ions. So this is going to be plus 3.000 times 10 to the minus 3 moles. All right, and we're going to be left with 0 moles of OH minus. It's the limiting reagent. We're going to end up with 1.000 times 10 to the minus 3 moles of the HPr, and we are going to have 3.000 times 10 to the minus 3 moles of the propionate ion. Okay, so now we have everything we need to do to solve this problem. We've got the number of moles of the acid and its conjugate base, and we've got the Henderson-Hasselbalch equation, our favorite equation. So this is going to be the log of number of moles of PR minus divided by the number of moles of HPR. Now remember I said, because we're dividing the volumes, it's a buffer system, so the volume is exactly the same. So concentration, the volume term is going to cancel out, so we can use number of moles, which makes this really easy. We don't need to figure out how many milliliters we added or anything. We just take the number of moles and we can directly calculate this. We don't have the pKa yet, but we do have the Ka from the problem. Right? The Ka from the problem is 1.3 times 10 to the minus 5. So that's the first thing we need to do. So the pKa is going to equal to negative the log of the Ka. So that's going to equal to minus log of 1.3 times 10 to the minus 5. Or in other words, the pKa is equal to 4.89. All right, so we plug into the Henderson-Hasselbalch equation. pH equals to 4.89 plus log of 3.000 times 10 to the minus 3 moles divided by 1.000 times 10 to the minus 3 moles. I'm keeping all these significant figures from the original problem. Remember, there's 4 significant figures here, 4 significant figures here, so that's why I'm keeping it here. So the pH is going to be equal to 5.37 for this case. All right, so we're in the middle of the buffer region. It has now increased some, up to about 5. Now, remember, this curve is not specifically for this reaction. This is a generic curve showing a weak acid, strong base case. But you see, we started this reaction originally at 2.94, and now after we have added 30 milliliters of base, that's part B of this problem, the pH is now 5.37. We have not reached the equivalence point yet, but we're in the middle of this buffer region, and because of that, we can use the Henderson-Hasselbalch equation. In fact, anything from the first drop past 0 all the way up to, not including, but all the way up to the equivalence point, we can use the Henderson-Hasselbalch equation. It's the far and away the easiest way to do it. The trick to this is we have created a mole table. Okay, we have the initial number of moles, the change in moles, which is basically a limiting reagent stoichiometry problem, and then we get the final number of moles of the acid and the final number of moles of its conjugate base, plug it directly into the Henderson-Hasselbalch equation, you can get the pH. All right, I'm gonna make one more video of this. We will do the equivalence point, which is 40 milliliters, and we'll do beyond the equivalence point.